Hey everyone, welcome to the irregularly scheduled Computer Science 3200 class on a Friday. Apologize that I had to reschedule this, but yesterday for some reason my voice was just gone, and so I really had to reschedule it for today. It's not 100% today, but definitely good enough to get through. So today we have a really cool lecture, which is about an introduction to neural networks. And in this lecture, what I try and do, there's a million tutorials out there for like what neural networks are and how to use them, and TensorFlow and Torch and all these programs that you can use. But what I want you to be able to understand is how a neural network actually works. And so that's what we're going to talk about today, like some of the underlying theory of why this thing should actually work. And also, just a reminder, in case you didn't see on Discord, Assignment 5 was released, and because I released it a day late, I gave you 2 extra days to submit it. So it's now due actually after the last day of classes, so it's due that Saturday. So you have 2 extra days. You can still submit it on the last day of classes if you want to, but just because I released the assignment a day late, I wanted to give you more time to work on that. Okay. So, let's get right into the lecture. And as I said, we're going to be talking about neural networks. Let's bring up the PowerPoint. Perfect. Okay. So, lecture 18, neural networks. If you've taken the biologically inspired or nature-inspired computing course, 3201, you probably will have covered this already, but you can't have an intro to AI class without talking about neural networks, right? They're all the rage these days, so much so that people have come to associate all of artificial intelligence with neural networks. But how did it get to this point? How did they become so prevalent and so powerful? Well, here's a story. Let's go back a little bit. In 2010, 10 years ago, not 50 years ago, 10 years ago, MIT, Massachusetts Institute of Technology, best STEM school in the world, if you want to look at it that way, was reviewing which topics that it should drop from its computer science artificial intelligence course to make room for more modern techniques. Neural networks were considering being dropped from that course in just 2010, okay? Neural networks had stagnated for decades. They've been around since like the late 50s, early 60s conceptually, but they had accomplished almost nothing in the last like 30 years. Nothing of meaningful value, right? So what they decided in this MIT AI course was they said, okay, there's a lot of historical value to neural networks. They show how you might be able to do something like possibly model the brain. And so what they did was they decided to just leave them in the course just because they could be something interesting, right? But not because they had been doing much in the last little while. And in the previous 30 years of research, neural nets, yes, they had some results, but it really wasn't the groundbreaking AI results that they wanted. And so what changed in the last 10 years? What changed to make neural nets to go from nothing to everything, almost? Well, in 2012, Geoffrey Hinton, out of the University of Toronto, published this paper, and it was Imagenet classification with deep convolutional neural networks. There were 60 million parameters in the network, and what you can look at parameters, not always are they just the weights of the network, but later on when we start to talk about the weights of a neural network, just keep in mind that this neural network had 60 million of those, okay? So the purpose for this was there's this competition which is called the Imagenet classification competition. And in this competition, you're given a bunch of training data, and I'll show some examples of that. And in the images, you'll get images with classifications, like this is a dog, this is a cat, this is a ladybug, whatever. And the purpose was you got this image, and I can't remember exactly how many images there are. There might be hundreds of thousands. There are 1,000 different categories that a given picture could belong to. And this paper and this method absolutely blew away the competition. It was crazy how much better this was than anything else that had come before it. So it combined neural networks, and so we'll talk about deep neural networks next time, but it combined the power and flexibility of neural networks with convolutions, and we'll talk about that next time as well. And whenever you see the term deep neural network, deep means many hidden layers. So as we learn what these hidden layers are, just keep in mind that a deep neural network just has many of those, okay? So here's an example of what this program was able to do. So here's some example images up on top where it correctly classified things, okay? So up here, you see that this image, its correct classification was might. So the correct classification is this one right here. Ignore these on the bottom for now. I forgot to take them out of this slide. So you can see here that what the neural network that they made computed was a probability of which of these categories, all the 1,000 different categories, it assigned a probability to whether or not that specific category was the thing that was in the image. And so you can see here that it thought might was the most likely thing, followed by Black Widow, followed by Cockroach. And so even the second and third place things that it thought were, they're kind of look like that thing. This one was a container ship, and it really thought it was a container ship. It was very certain of that, but then went to like lifeboat as the second place thing. Over here we have motor scooter, so it correctly classified that. But you can see that not only is it correctly classifying things, but the other things that kind of look like it also says, okay, there's like a non-zero probability of these being it, right? So all around, it's doing really, really well. So for example, here it thought this was a leopard, or it could have been a jaguar or a cheetah with a smaller probability. On the bottom here, I've actually expanded the bottom one to these examples where it got things wrong. And in my opinion, the things it got wrong were scams. Like, I don't know why they had these images labeled like this in the data set, but it thought that this image here was a convertible. But what the actual image was labeled as was a grill, and the grill is the front thing on a car. But I mean, come on. It is a convertible. It's just that the human who labeled this was showed the entire car instead of just the grill. Here, the correct label was mushroom, but it just barely thought that this should be agaric over mushroom. And it turns out that agaric is a specific type of mushroom, right? And so it was very close on that one. For this image was labeled cherry for some reason, but it thought it was Dalmatian. Of course it would think it's Dalmatian. There's like a Dalmatian in the picture, right? And this one thought it was it's a Madagascar cat, but it thought it was a squirrel monkey or a spider monkey, which is pretty close, right? So even where it's getting it wrong, it's just barely getting it wrong. And so this paper was actually quite revolutionary in terms of its capabilities, okay? So what it did was, and we'll see next time when we talk about deep neural networks, it took the idea of neural networks and scaled it up using GPUs in a way that had never been done before. Okay. So, also, which we'll talk about in a future lecture, deep neural networks have been key in a lot of recent successes in AI for game playing as well. So this is Alphago. Alphago is a system created by Google DeepMind that recently beat the world champion at the game of Go, and it used deep neural networks at its core. Also, this is the Poker AI group out of the University of Alberta, and they use deep neural networks to help beat humans, the world champion humans at poker as well. So, neural networks, how do they work? Okay? This is pretty much how most people view neural networks, right? This classic comic where it's like, okay, we have some mathematics and then a miracle occurs and then we get the output, right? But neural networks are not magical. They are math, right? And because they're math, we can explain them. But before we explain them, let's go into a little bit of the motivation for neural networks and why they came to be and how people have used them. Okay. So let's look at the difference between a standard computer and the human brain, okay, in terms of hardware. So, the number of processing units that a standard computer has is somewhere around 1 billion, right? 10 to the 9. Whereas the brain has approximately 10 to the 11 neurons, okay? And neurons, of course, are different than transistors, but we'll see what neurons are in the next slide. The storage capacity, you could have, terabytes or possibly petabytes of memory in a computer. The brain uses those same neurons and the synapses between them in order to store data, right? And so they have 10 to the 14 possible synapses, and of course this doesn't mean that if I have one number of neurons and synapses, this means that's exactly this number of bytes. It's just sort of comparing the hardware at an abstract level. The processing speed of a standard computer, the clock cycles are actually much faster than they are in the brain, right? So you've got like a 100 millionth or a billionth of a second in a computer. So you've got gigahertz that you're talking about in a computer, versus in the brain, you're talking about like millisecond type processing speeds. And the bandwidth is really where there's a huge difference. You've got about like a gigabyte per second, or maybe tens of gigabytes per second nowadays in computer hardware bandwidth, whereas in the brain, it's got like terabytes per second, because all of these neurons and synapses in the brain are actually operating in parallel, right? So there are definitely differences in the hardware and how that hardware operates, and the brain is this like massively parallel thing, whereas computers still, even though we're talking about, nowadays we might have 64 cores in like the top end AMD CPU, for example. Well, you certainly don't have 10 to the 11 cores, right? So let's not get ahead of ourselves. The brain is a much more massively parallel thing. Okay, so here's an abstract schematic of a biological neuron, and this is what the brain is really made out of, okay? So here we have a neuron, and again, I'm not a biologist, so please don't hold me if I make a small mistake here. But here we have like the cell nucleus, we have these dendrites, and the dendrites can be considered as inputs, okay? You have this sheath that goes out to axon terminals, and you have this axon here, which is the sort of dangly bit at the end. So the whole point that I want you to look at here is not necessarily know all the biology, but what we have here is we have these dendrites, which are the input signals to the neuron, and then we have these axon terminals that are the output signals of a neuron. And these output signals are going to be connected to the dendrites of other neurons, okay? So, what is the neuron? The axons from one neuron extend to the dendrites of another neuron. So here we have these axons, and what you'll see is that we're going to have other neurons over here, right? And the axons of one neuron are going into the dendrites of other neurons. So this kind of feeds back around, not to itself, but to the inputs of other neurons. Stimulation of the dendritic tree, and this here is the dendritic tree, okay? That first part. Stimulation of this with some electrical signal may cause the axon to spike like a transmission line. After firing, the neuron will go quiet for a while, so it has some refractory period. Firings can affect surrounding or connected neurons and cause some sort of chain reaction. So I'm not going to get too much into the brain because A, I don't know a lot about it, and B, all you need to know is that the artificial neuron that make up neural networks mimics this process in some way. That's all I want you to know, okay? Is that it is biologically inspired by a thing that actually exists in our own brains. That's really the important part. So, let's look at the very, very first implementation of something that looked like an artificial neuron. And what I don't like about some videos about neural networks online is they don't go this far back. And you really need to go this far back in order to understand exactly what's happening inside a neural network. So these were called threshold logic units, or TLUs. And this is how they're made. So a TLU is going to have a bunch of inputs They're binary inputs, okay? So down here, we can see that we're going to have a bunch of inputs, x1 through xn, in this column. You're also going to have a number of weights. And so these weights are going to be real valued. So whereas the inputs were binary, on or off, right, 1 or 0, these weights are going to have real values. Then what happens is the inputs, so the first input gets multiplied by the first weight, the second input gets multiplied by the second weight, and then they all get summed up, okay? And if that sum is a given threshold, then the output is a 1. If it's not, then the output is a 0. So if we look at this this diagram over here, we have something that sort of looks like that neuron, right? We have inputs and we have an output. And here's how it looks like in terms of like an actual formula. So our output y is going to be, well, what we're going to do, we're going to take each weight, so wi to wn, we're going to multiply it by the input xi to xn, right? And we're going to sum all of those. So you take each input, you multiply it with its corresponding weight, and you sum that value. If that value is greater than or equal to this theta, which is a threshold, okay, then the output is 1. Otherwise, the output is 0. So that's what happened in a threshold logic unit. And just to let you know, if you take each element of one vector and you multiply it by each element of another vector and you sum all of those, that's called a dot product. Okay? So if the dot product of the input vector and the weight vector is greater than the threshold, then the output is a 1. Okay. So let's look at what these threshold logic units can actually do. Okay? So let's say we want to compute the logic, so the Boolean logic for a Boolean formula. So up here, we're looking at the Boolean formula x1 and x2. Okay? So what we want to do is we want to construct a threshold logic unit which can take in two inputs, x1 and x2, and we're going to put the weights and the thresholds onto this TLU so that the output will be 1 if x1 and x2 is true, and the output will be 0 if x1 and x2 is false. And you may be saying, how the hell does this have anything to do with neural networks, Dave? Trust me, okay? Trust me, it will. So, what we can do is let's assign the following weights and the threshold to this right here. So let's give W1 a value of 3 and W2 a value of 2. And we'll have our threshold be 4, okay? So if x1 and x2 are both 0, what is the output of the function? Well, the function is 3 times x1 plus 2 times x2. So we have that function listed here, right? And it says if the output is greater than 4, then y is 0. Or sorry, y is 1. If it's less than or equal to 4, then it's 0. Okay, so if both are 0, then this is obviously 0, and that's not greater than 4, so y is 0. If x1 is 1 and x2 is 0, then the output of the function, or the TLU, is 3, and that's not greater than 4, and so the output is 0. Next, x1 is 0, x2 is 1. The output of the function is just 2x2, so it's 2, and so that's not greater than 4, and so the output is 0. But down here, when x1 and x2 are both 1, then 3x1 plus 2x2 is equal to 5, and that is greater than 4, and so the output is 1. And so what we've done here is we have assigned weights to this TLU such that it now computes the Boolean formula x1 and x2. Because of course, the Boolean formula x1 and x2 is only true if both the inputs are 1. See how that works? So that's a threshold logic unit. And not only that, but look at this over here. So here is a graph of these input values. So on the bottom, on the x-axis, we have the variable x1, and on the y-axis, we have the variable x2. So we're just going to plot points on this graph for the values, the different values in the truth table that we could have. So we have 4 different possibilities. We have 0, 0, 1, 0, 0, 1, and 1, 1. So these are those 4 points, right? 0, 0, 0, 1, 1, 0, and 1, 1. And if you plot them on a point or if you plot these points on this graph, and then you say color it black if it's true and color it white if it's not true, then what does this line here, what does this function actually mean? Well, that function, we can very easily convert it into y equals mx plus b form, right? And what we get is the equation of a line. This is really important. The function that we get from the threshold logic unit of 2 inputs is the equation of a line. Now, that line, what it does is it separates the plane. And it separates it into the things that are true and the things that are not true. See how it does that? So this one line separates the plane into things that are true and things that are not true. Okay, that's really interesting. Now let's look at implication. All right, x2 implies x1, and of course this logic formula is equivalent to like not x2 or x1. But the same thing happens. Okay, so we're going to come up with weights here, and those weights are going to be 2 and negative 2. And so if 2x1 minus 2x2 is greater than negative 1, then the output is 1. Otherwise, the output is 0. Okay, so I won't go through all the math here, but what you get in the end, again, this is the equation of a line, and if you plot the equation of that line, you get the line which separates the plane into truths and not truths. Okay, see how that works? So this equation is able to separate the plane into values that are true and values that aren't true. And so essentially what threshold logics are doing are just separating some dimensional space by a linear chopping, okay? So this 2-dimensional space would be separated by a line, but if we had a 3-dimensional space, okay? So for example, if we have 3 Boolean values and we want to estimate this big ol' function right here, we could come up with weights that try and make a threshold logic unit to separate, because there's 3 values now, our graph would be 3-dimensional. And so the formula we come up with, 2x1 minus 2x2 plus 2x3 greater than 1, that will be the equation of a plane. Okay? So threshold logic units like this, they take the number of inputs, that dimension, and they draw a linear structure of dimension n-1 through that place, okay? And here, we happen to come up with the weights that match the outputs of this Boolean formula. So that's what these threshold logic units are doing, okay? In the case of 2 inputs, we're drawing a line through a plane that separates the truths from the not truths. Okay. So now that we've done that, we can understand the concept of linear separability. All right? Linear separability is the key to neural networks. So we call 2 points in an n-dimensional space linearly separable if they can be separated by an n-1 dimensional hyperplane. One of these sets may contain points on the hyperplane. A Boolean function is called linearly separable if the sets of points of 0 and the sets of points of 1s, so the trues and the falses, are linearly separable. Okay? So n-1 dimensional hyperplane, that just means that, for example, if you're in a 2-dimensional plane, it's separated by a 1-dimensional line. If you're in a 3-dimensional dimension, then you're separated by a 2-dimensional plane. Okay? So you take whatever space you're in and you cut through it with a linear structure, whatever that is for that dimension. So consider now, when we're talking about linear separability, we've looked at all the good examples so far, right? So now we look at by implication or equivalence. And by implication, the truth table for that, or the equivalence truth table, is really easy. If they're both the same, then it's 1. If they're different, then it's 0. It's the opposite of XOR, right? And so if we look at the plane for this, look at this. So if x1 is 0 and x2 is 0, of course they're the same. If x1 and x2 are both 1, they're the same. But where they're different, the output is false. So my question to you in the chat now is, where can I draw the line to separate this plane into trues and not trues? Someone tell me. Where do I draw that line? Someone out there knows, right? You can't draw a line, right? No matter where I try and draw a line through this plane, I'm always going to have trues and falses on one side of the line. So for example, I could try and draw a line here, and okay, I've separated this one true, but now there's trues and falses on the other side, right? In order to be linearly separable, all of one type has to be on one side and all of another type has to be on another side. And you can't always do that. In fact, the number of times that you can do that is remarkably low. Okay? So let's have a look at this table. Look at these are the number of inputs that we have to a Boolean function. So let's say we have x1, x2, x3, x4, all the way up to some value of n. So here are the number of possible Boolean functions that we could have with this many different inputs, right? So when I talk about different Boolean functions, we could have like, let's say we had 2 inputs. We could have x1 and x2, x1 or x2, not x1 and x2, not x2, or, you know, you could have all possibilities of all Boolean operators on 2 functions. And so, if we look at this, well, all functions of input size 1 are obviously linearly separable, right? Because you can draw a line and they're all on one side because there's only one variable. However, when you go up to 2 Boolean functions, still most of them are linearly separable, okay? So for example, the one we just saw, which is now all marked up, this by implication one, that's one of the 2 examples that's not linearly separable. I'll leave it up to you as an exercise to tell me which is the other function of input size 2, which is not linearly separable. But if we look, as we go up and up in variable size, the trend is that, like, for example here, we have 4.3 billion, I think that's what that works out to, or 400 million, or whatever 10 to the 9 is. We have this many possible Boolean functions, and we only have 94,000 of them, which are linearly separable, right? And so for many, many, many inputs, for the vast majority of possible Boolean functions, a single threshold logic unit cannot compute those functions, okay? And that means it cannot draw a line through that it cannot draw a hyperplane through that space to cut all the falses and all the trues. And so what you need to do is create networks of many TLUs to overcome that, okay? So let me just, I gotta discard the drawings from here. Okay, so what that means is, what we could possibly do is we could say, okay, let's chop up the plane with a bunch of TLUs, right? So now we've separated it so that, you know, we've got all of one class in like one area, and so now we've chopped them all up, right? And then maybe we could do something with that. So what they're saying is, if something isn't linearly separable, if we use multiple TLUs and somehow combine them, then maybe we could classify things with them, okay? So that's what a TLU is. Let's go on then to the next iteration, which was called the Perceptron. I love the Perceptron. It's like such a good name. I wish like Honda made a vehicle called the Perceptron. I'd definitely buy it. And so the Perceptron is like an artificial neuron. It's the simplest form of an artificial neuron. Okay, so give me 1 second. I gotta ban some spammers in the chat. There we go. All right. Yeah, it'd also be great for a mobile phone. All right. So now we're moving on to the artificial neural network, and it is very, very close to a threshold logic unit. It's like the next step, okay? So, in a perceptron, what you have again are you have some inputs, right? Forget this 1 for a second. You have some inputs, x1 through xn, and you have some weights, x1 through xn, just like the threshold logic unit. However, now these inputs can be floating point numbers, okay? They don't have to be booleans. You do the dot product of these, so you multiply each of the inputs by each of the weights and sum them up. So that's the dot product again, okay? So for an exam, you should know what this is. You may have to compute the value of a neural network, you never know. However, instead of passing that value over a threshold, like a simple threshold to say that, hey, is this value greater than something, we pass it through an activation function, okay? And that activation function just takes the place of the thresholding. So as before, where the thresholding was like an if statement, what we have now is this activation function. And so how does that activation function work? Well, let me draw a little diagram here. Oh, crap. I wanted to go below that. Okay, 1 second. Okay, I'm going to try and draw this here. Oh, we go back. Okay. So I'm going to draw my axes here. All right. So let's say in a TLU, I had a threshold of 0. Okay. How would I represent that as a function? I could obviously do it as an if statement. That would be really easy. Like if the value is greater than 0, it's 1. If the value is not 0, then it's 0, right? So what I actually want is a function that looks sort of like this. So this is x equal to 0. This is the negative x-axis. This is the positive x-axis, right? This is like negative 1 right here. This is positive 1 right here. So let's say I wanted it to be like negative 1 if it was below 0 and positive 1 if it was above 0, okay? So what I would do if I look at this as a function, then I would say, okay, over here we're not greater than 0, right? But as soon as x becomes 0, then I want my value to be up here, right? And so that's what this function up here, this one, is doing. It's a functional version of an if statement, if you want to look at it that way, right? So it's just saying this function is a step function which says if the value is below a certain value, it's this output. If the value is above a certain value, it's this output. And this has this like infinitely sharp jump right in the middle and then goes over. Okay, so that's what this activation function does. It's essentially the thresholding. But by replacing it with a function, we make it more powerful, right? Okay. So again, remember what we have in the brain, right? We have inputs that go into the dendrites, and those inputs make something here fire electricity, and those go to the outputs, which then go into the dendrites of other neurons. Perfect. Okay. What if we looked at what the brain is doing? Okay? Because these biological neurons do not live by themselves like threshold logic units. What does the brain do? Well, as we just said, the outputs of some of these neurons go into the inputs of other neurons. And so what the brain is doing, and this is obviously simplified, right, is it has some inputs, it's got some network of things, of neurons and synapses between the neurons happening inside, and it's going to produce some number of outputs, right? And so here, what we have is like the mathematical function of the brain. This is not the function of the brain, but this is how we're representing this from now on, okay? So we're going to have the output vector y, because the output is not a single variable anymore, right? Before it was just y, now it's a vector of y's. And so this here, this little bar, that means a vector of y's. That vector of y's is now a function of an input vector, a weight vector, and a threshold vector. Okay? Because the thresholds, you need a threshold for each of these things, and so there's an input vector of inputs, there's a vector of weights, and there's a vector of thresholds. And you know what all of those are now. So let's do that with our neural net. Okay? So this is what a neural network is. It's a bunch of these artificial neurons where we have layers. So you can view them, typically they're viewed from left to right. So here we have our inputs, okay? X1, X2, X3, X4. Those are our inputs. And those inputs are going to go into the first layer of neurons. So these are all identical neural networks, except each of these lines here is essentially going to be a weight. So whenever you see a line in a neural network diagram, that line is saying that this input, so the output from this node, is going to the input of this node. Okay, and by node I mean neuron. So the output of this is just an input, so it's not technically a neuron, but the output of this, which is just its value, goes into the input of this neuron. And then the outputs of this neuron go to the inputs of these neurons. And the outputs of this neuron go to the inputs of these neurons. Okay? So it's a network of neurons. It's a neural network. And that's what it is. And each of these lines has one of those associated weights where the output of this neuron gets multiplied by this weight, right? And then it passes through an activation function and is now the input of this neuron. And that's all a neural network is. It's a bunch of those very simple neurons tied together. So, and at the end, the outputs of these are somehow tied together, and then you have actual outputs. So whether those outputs are, Booleans or floats, usually they're floating point numbers, that's what comes out of the end of this. So now that we have this, what do we mean when we train a neural network? Because before, what we did was, when we go back to our threshold logic unit, is we somehow magically came up with these values, right? I said, we can find weights such that this function works. But how did we find those weights, right? We don't want to create a big neural network and then sit down and manually figure out the weights such that all of these computations happen to come out to be the output that we want. So how do we go about figuring out the weights for a neural network? Okay, well, this process of figuring out the weights is called training. So the way that you train a neural network is that you're given some input data and some known outputs. So if you recall back a few lectures, this is supervised learning. So for the vast majority of cases, neural networks do supervised learning, okay, where they're given some inputs and correct known outputs, and then what they're going to do is they're going to somehow figure out the weights that will make the input match the known output. So running the inputs through the network gives us a calculated value. So that calculated value is this y vector, okay? And by the way, I'm seeing all this discussion in the chat. I love it, but none of it's relevant to what I'm saying right now, so I'm not going to be answering those questions. So if we run the inputs through the network, it gives us a calculated value. It gives us this y vector, and that's a function of all these inputs and weights and thresholds for all of our different neurons. That's called feed forward. So if you've ever heard of feeding forward through a network, if I take this network and I pass in some values here at the beginning, and I do all of these dot products and all of these calculations, and then I eventually get an answer out the end, that's called one feed forward. So we feed the inputs in, they are passed forward through the network, and we get an output. That's a feed forward of the network. Training a neural network then involves tuning the weights and thresholds until the values we get out of the network match our training data, right? So, for example, if we passed in some inputs and the correct output should have been 5, but the output that we got was 1,000,000, then we're going to want to tune our weights somehow so that that answer starts getting closer and closer to the correct value of 5, right? So that's what training does. And so a neural network at its very core is a function approximator, okay? we have inputs. The inputs should really produce a given output, right? And what the neural network does is it tries to somehow fix the weights so that the output that we get is the correct one. And so if you black box away all of this stuff, a neural network is just a function approximation device. It's trying to get proper weights so that the output is matching what the output should be. Okay, so training progress. Let's have a look at this. Let's say we have some desired function, d, okay? So d is our desired function. That's the actual function. That's the actual function that we're trying to approximate somehow. So this would be like the oracle function that tells you whether or not an image is an image of a dog or a cat, for example. So this output, d bar, that's the actual outputs of like the actual real world function that the neural network is trying to approximate. And that is some function of the inputs, right? The neural network function, which we want to approximate the desired function. Oh, 1 second. I got some notifications turned on that I want to turn off real quick. Okay. Let me go back. All right. So the neural network, we want to approximate the desired function. Okay, so the neural network is a function of the inputs, weights, and thresholds. So whereas the actual function, you just need the inputs, right? Like if I'm trying to calculate let's say I input the speed and velocity and weight of a baseball bat, and the output is how far the ball travels, right? The actual universe only needs those inputs, but the neural network needs these weights and thresholds. So the performance of my neural network should then be a function of the desired vector and the calculated vector. And what that means is I'm going to measure how well my neural network is performing by computing the difference between my neural network's output and the true output. So let's try vector distance, for example. So, for example, if we take the differences between all of the real answers and all of the approximated answers from the neural network, and then we square that, then that's the sum of squared differences, okay? So some error calculation which tells us how far our approximation is from our true values, that's what we're going to use to measure the progress of the training of the neural network. And hopefully, we want to get p equal to 0. We want the outputs of our neural network to exactly match the outputs of our desired function. Now, sometimes we don't get to exactly 0, right? But we're trying to minimize this over time so that our neural network more closely approximates the desired function. So how in the hell do we adjust these weights? Right? How in the world do we adjust weights? That seems like a magical thing, and it's still kind of magical to me. This is where you get into calculus, and calculus is magic, right? So let's say we have some weights, W1 and W2. So this over here, this is kind of hard to see. On the x-axis, we have W1, and on the y-axis, we have W2. So over here, what you're seeing inside this graph is sort of if we have one weight at a specific value and another weight at a specific value, the length of the vector here is sort of how big the error is. Okay? So for example, if we randomly chose this weight right here, so x1 equal to, or w1 equal to this value, and w2 equal to this value, and so we got this point, it looks like the arrows are pretty long there. And so that's just a representation of the error. Okay? And what we get is some performance contour. And what these lines represent is some performance contour. And out here you can see, well, the arrows are quite large, and so the errors are big. But as we get to the true desired values of W1 and W2, those values get very small. The errors are very small, okay? All right. So, at any given time, we are at a given point in this contour space. And what we want to do is we want to find us the action that brings us toward this minimization of the error vector, okay? Ideally, we want to go in the direction of error that brings us minimal, okay? So what could we do? Could we use hill climbing? Well, that's kind of intractable in a lot of cases. What we're going to do, I won't go into every possible way that you can do this, but the most popular way is called gradient descent, okay? So let's look at gradient descent from an abstract point of view without getting into all the detailed math. Let's look at gradient descent over here on the left, and remember, we're actually doing this in multiple dimensions, right? It's not just W1 and W2. There's like an n-dimensional space where n is the amount of inputs that you have. So let's look at it in sort of one dimension in order to explain how gradient descent works at an abstract level. So over here on the y value, we have our on the y value. On the x-axis, we have our value of w, which is a weight. Based on the value of this weight, we're going to have some error over here. I forgot to label that, okay? So if this is the error when we have the initial weight, what we can do is we can take the output of the error, which will actually be a vector, and we can find this derivative. Okay, so we're going to find the derivative at that point on this curve, and we're going to follow in that direction. And what that means is if the error says I should go in this direction, or if the error is going down in this direction, then I should pull my value of w by that much to the left. Then I'm going to try again, and now maybe I'm at this much error, and then I'm going to pull w over to the side again. And I'm going to keep going and going and going. So what we have here is at every point I take this gradient, right? So I take the tangent line. The tangent line in multiple dimensions is called a gradient, okay? So here I'm taking these tangent lines, and whatever the slope of the tangent line is, I'm moving my weight in that direction. So what we get is that if we have some starting point, like this, over here on the right, I have a starting point, I find the slope, I move my weight in that direction, I get a new value, I find the slope, I move it in that direction, and eventually I'm going to converge to the minimum error, okay? So this is the error curve, and I will go down in this valley until I get the minimum error curve. The problem arises, though, is that this may not be the globally minimum curve, right? So the process of gradient descent finds a locally minimum. So it finds a local minima or maxima, depending on if you're doing gradient ascent or gradient descent. But usually it's gradient descent. So we can find this spot really easily, but we may not find the global minimum. So let's look at this in many dimensions, okay? Let's say that we started in two different points, this point here and this point here. I know that the red kind of matches, apologies for that. So if we did gradient descent, and we can do this in multiple dimensions, not just one dimension, okay? So we find the slope, so in this case it would be a plane, and we modify our values in each of those dimensions so that we're going down the curve. And so what you see in this case is where we go down, 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 we follow these gradients to get here. But if we were just a little bit over to the left, or a little bit over to the right, maybe we would have gone to a completely different local optima, okay? So this is one of the problems with gradient descent, is that sometimes it doesn't find the globally best answer, all right? And there is no good solution to that. If you could solve this problem, you'd be a quadrillionaire, all right? Every neural net would always converge, and you'd be fine. So, at a very high level, without getting into multivariate calculus, gradient descent calculates the derivatives based on the errors, the update function, so the change in the weights is just that derivative, okay? And then you update the weights based on the partial derivatives of each of those things. However, the only reason I'm showing you this calculus is not because I'm not going to have calculus on the exam or anything like that, is to show you that we do need to take derivatives. And that's important, because in order for gradient descent to work, this error function, p, has to be differentiable. It has to be differentiable. And so if we go back to the neural network, to the neuron, the problem here is that if we are using this threshold or this step function, is that function differentiable? Right? So this function, this error function, relies on this step function for the activation function, and the problem is that is not differentiable. Okay? And so if that function is not differentiable, then we can't really say anything about the convergence of our gradient descent. And so it doesn't work. So what can we do? Are we going to give up? Well, obviously we didn't give up because we have neural nets that are performing really well. And so what we're going to do is we're going to take this simple neural net, this simple neuron, and we're going to try and somehow make it compute the same value, but by removing the threshold. So let's remove the threshold. So thresholding makes our function non-differentiable and also really annoying to compute. Ideally, what we want is instead of our function, our outputs being a function of x, w, and threshold values, we want it to just be a function of f of the inputs and the weights. So we want to remove the thresholds from the equation. So what we're going to do is we're going to introduce something called the bias neuron. Okay, what is the bias neuron? The bias neuron helps us to eliminate thresholding in one way and makes neural nets a little bit more robust. So we're going to add an extra neuron to each layer called the bias neuron. It's going to have a fixed value of 1, and it's going to help us by having a similar effect to that of thresholding while being easier to compute. Okay? So, how in the hell does that work? Like, why does adding an extra neuron do anything? Well, here's how that works. Over here, we saw the threshold logic unit where we have inputs multiplied by weights and thresholded. Okay? We threshold them here. Instead of doing that, we can make this threshold always be 0 and remove the thresholding by introducing a bias neuron, x0, with a value of 1 and having its weight be negative theta. So the outputs of these two functions are the same thing. So instead of checking if the dot product is greater than or equal to the threshold, we can check if the dot product minus theta is greater than or equal to 0. Now you might say, Dave, that's just semantics, like you're just moving this over. But the good thing is, if we make this threshold always 0, we have some really interesting mathematical functions that can compute this in a non-discrete way. So, we're going to smooth the activation function. So, step functions are non-differentiable. So, we're going to approximate the step function. So, for example, this step function or this sine function, which is non-differentiable, with something called a sigmoid function. And a sigmoid function has the property of looking and behaving a lot like a thresholding function, but it's smooth and continuous and, most importantly, differentiable. Okay? So if you've ever seen a neural network and it has a sigmoid activation function and you have to choose a different activation function, that's why the activation function exists. Okay? So before, all the other tutorials would just say, oh, you got to choose ReLU or whatever. Like, they're not telling you why that matters. This is why that matters. Is because you got to get away from these discrete step functions into a smooth sigmoid. Doesn't have to be sigmoid, but sigmoid is one possible activation function. So, step functions are non-differentiable. You can apply a sigmoid function or another function that looks like a sigmoid function in order to do that. So for example, this function here has this equation, and you can apply it and get an output. Okay? So that output may no longer exactly be 1 or 0, right? It might have values in between that, but ideally this curve is going to be pretty steep, and so only really near the threshold will you be getting non-zero values. So there are lots of different functions that you can use for the activation function, okay? And so, for example, all of these different functions here, which look very, very similar, all have vastly different functions. So if you use tanh or arctan or whatever function, or relu, or whatever activation function you choose or is best for your particular purpose, this is why you use it. Okay, and this lecture is about the why, not about the how. So the improved neuron now looks like this. You've got your input x's, you've got your weight values, you've got your bias neuron with a value of 1 and its weight. You compute the dot products of those and you sum them, and then you pass it through an activation function, whatever that activation function might be. This is just one example, and then you get your output. So that is the new improved neuron that we use in our neural nets. Now, when it comes to the structure of a neural net, what we have is the following. And you've seen a neural net already, you kind of know its structure, but this is the syntax of that structure. So this is the terminology. You're going to have an input layer, which comes from your data, right? So if you're playing, I don't know, a video game, this might be the positions of units. If you're computing a function, this is your x value, your y value, whatever. So these are your inputs. Those inputs are passed into neurons inside a hidden layer. And then you have an output layer which contains your outputs, right? So that might be like all the different categories with a percentage of whether you think this is a dog or a cat or whatever. But the important part here is that there can be more than one of these hidden layers. And they're called hidden layers because I don't actually know why they're called hidden layers. Probably because it acts sort of like a black box, right? Because all this math is so complex in the middle. Even though we understand it all, it's hard to keep track of it, maybe. I don't know. It's hidden from the input. It's hidden from the output. Anyway, doesn't matter why it's called a hidden layer. It just is called a hidden layer. And here's an example of something like that. Okay. So a common structure is that all of these are fully connected. So fully connected means that every neuron from every layer, all of its outputs go to the inputs of the next layer, okay? So that means fully connected. If we start with a fully connected network, then unimportant connections will eventually train to a lower weight. But the network can have an arbitrary structure. And some research has done things like, hey, let's learn the network structure from genetic algorithms or whatever. So what does this mean? It means that, we could have a fully connected network in which all the outputs from these go into these, like this, right? So we have all of these, but we could delete some of these connections as well. But the point is that if we do have a fully connected network, and these connections weren't really contributing anything to our output, then after a while, then these weights will just be 0 anyway. Okay, so a fully connected network can simulate a non-fully connected network in that case. It's just that it will take longer to train. Okay, so there's an incredible, one of the best tutorial videos I have ever watched is this one. So screenshot this link and then go there and watch this afterwards. It's the complete from the ground up implementation of a neural network in C++, and it was really only after watching this video did I really understand how a neural network operates and how it is made, okay? So please go watch that. It's excellent. It's a really excellent video. But what we're going to do now is we're going to do a demo of a neural network online. So let me load that up. So playground.tensorflow.org, you can go there and play along as I explain things, and it's quite a great demo. Okay, so let me make my camera a bit smaller. That's not my camera, this is my camera. Here we go. So if you load up this website, here's what you get. And what we have is, let me just explain this interface. So here on the left, we have a bunch of different inputs, okay? And we have some neurons, and then we have outputs. Oh, sorry, we have 2 hidden layers here. So let me subtract. There's only 1 hidden layer now. And then from this hidden layer, you get the output. So let's load up this training set of data. And what this training set of data does is that we have some input x1s and x2s, okay? And we want to classify all the points that are orange and all the points that are blue based on the input values. So if we run our neural net, what we're going to see is that it has correctly classified this section as all the orange points and this section as all the blue points. So after you run it, what you see in real time is that you're computing the areas of the graph that it thinks should be classified as orange points and the area of the graph that it thinks should be classified as blue points, okay? So in this case, we had 2 inputs, we had 4 neurons, and we pressed the button, and the training, now this is doing the gradient descent behind the scenes, right? And it's coming out with this. But, for example, how did I choose the structure of this network? How did I know to use one hidden layer with 4 neurons? How did I know to use all these learning rates and stuff? So we're going to ignore the learning rate stuff up here for now. And what we're going to do is we're going to logically think through something. So think back to when I said what a threshold logic unit did. So a threshold logic unit, or a neuron, if you want to say, a neuron is not exactly the same, but it does kind of the same thing. A single threshold logic unit with 2 inputs, what did that do? It drew a line through a plane, right? So, if I look here, if I look at this set of data, I have orange points here, and I have blue points here. Can I draw a single line through that plane which categorizes both sets? So say in the chat, is there a line which exists through that plane that categorizes these sets of points perfectly? Is there a single line? Well, I kind of spoiled it for you. There is, right? So if I draw a line like this, then it will categorize both points. Someone even gave me the equation of the line. That's great. So what that tells me is, if these 2 categories of points are linearly separable, then I should be able to have a neural network with a single neuron that separates them. Because one neuron is going to draw one line through this plane. So let's run that. I have a single neuron. I'm going to run my neural net. And what it does is it finds the weights through gradient descent. Okay? So if I look at this, you can actually mouse over and you can see the weight is equal to negative 2.1 over here. These weights are equal to negative 0. Whatever. And so what we get out is the function. Remember the threshold logic unit function where it was like 2x2 minus 4x1 is whatever? Well, this is the function that we now get that separates these 2 points. That's awesome. That's really cool. Okay. But because neural networks are so great, if we did have more neurons and more hidden layers, it will also find that line. It's just that it may take a little bit longer to train because there are more weights. Okay? So, let's do something more interesting now where I want to do the following. Okay. So here, let's try and run. I'm going to have this point where we have a bunch of blue values inside a bunch of orange values. Okay? So I have a bunch of blue inside a bunch of orange. Well, if I run a single neuron, well, a single neuron is only going to be able to produce a line, right? So it's really funny, actually, watching this thing try and train itself to the optimal line to try and separate these. Okay? So, here's a question for you. If I want to completely encircle a bunch of points on a graph, what's the minimum number of lines that I need to do that? What's the minimum number of lines I need to encapsulate an area on a plane? What might that be? 3, right? We draw a triangle. So let's just try 3 neurons and see what happens. Okay, so Oh no, I forgot. Hang on. So what this does, is this an error or is this just me? Let me reload this. Apologies for that. Okay, let me run this again. Here we go. Okay, so remember how that was a good example. Remember how I said that sometimes we find a local minima? That may have been one of those local minima. So I trained it for several seconds and it didn't find it, okay? So based on your initial weights, which are usually chosen randomly, you could just not find your answer. And that's really just a shitty thing about neural networks sometimes. But here, if you look, what we kind of have is, if you can see, this is like a triangle with kind of flat sides and rounded edges, right? If I discretize the output down here, you can see this a little bit. Maybe this is actually better. But you have one line going this way, one line going this way, and one line going this way. And what we've done is we've actually separated these points, right? So if we draw this line, and this one, and this one, what that does is it draws the three lines, and then the outputs down here, the weights of the outputs of each of these, it's going to find outputs for those that says, if it's above this line, it's probably orange. If it's above this line, it's probably orange. Above this line, it's probably orange. And the same thing with the blues, okay? So, now, let's move on to a different set of points, okay? If we look at this, how many lines do you think we will need to separate this data, right? So we've got blues here, blues, and blues down here, blues up here, etc. Okay? I'm going to guess, let's say if we could make 2 lines. Uh-oh. I don't think it is 2 lines. I think it might be 4. Right? Let's reset the training. So this might bend around to eventually sort of... There we go. Okay, so we found one, right? Because we need a line here, a line here, a line here, and a line here. The reason we can't just have 2 lines, remember? We can't just have 2 lines here, even though we could separate them, like, graphically. So if we have one line going down the middle here, there'd be some orange and some blue on the side of one of those lines, right? And so we need these lines to form these sort of sectors here in order to do that, okay? So that's a little bit confusing. But however, this is basically how neural networks are working, right? Is they're drawing lines through stuff, and these are the lines, you can visualize it here, these are the lines that get drawn, okay? But what I want to do now, someone asked, why is the output not symmetric? The output is not symmetric because each of these have their own weights, okay? And so each of the lines has their own weights, and so the weights are just being learned by this gradient descent. Okay, so I chose 4 neurons because there was 4 lines. But what if I add another hidden layer? What does adding hidden layers do? Okay, well, when I added these when I added these neurons to the only layer, what this was doing, it was taking the input x values and taking the input y values and forming an equation of a line based on those input values. If I add another hidden layer, what it does is it takes the equations of these lines and forms in that space lines separating these lines. So it partitions the space of a partitioned space. And so what adding more hidden layers does is it allows us to find patterns within patterns within patterns. And that becomes quite difficult to visualize, but this is combining the outputs of these within its own linear I don't know how to explain that. It's this layer was finding patterns on the previous layer, the next layer finds patterns on its layer. Okay? So that essentially, if I'm trying to figure out like recognize faces or whatever, maybe the first layer does edge detection. Maybe the second layer figures out, okay, two lines like this. And then maybe the next layer is figuring out like the shape of a nose or the shape of a mouth. And then at the final layer, you take like the eye detector and the nose detector and the ear and the mouth detector and you weight those together and you say there's a face. So that's a very hand-wavy way of explaining what's happening when you have multiple layers. Now, let's go back to this example, okay? Because there's also another very important thing that we have to look at. So in this example, we had our x input and our y input, just the linear input on the x-axis and the y-axis, and we said we need 3 neurons because we have to draw these 3 lines in order to separate those shapes, right? However, what we could do is we could shape our input data to transform the space that we're trying to learn in. So for example, here we are passing in the x and the y values. What if instead we passed in the square of the x value and the square of the y value? Well, let's see what happens here. Let's have a single neuron. What's the equation of a circle? It has an x squared and a y squared. And so we're basically working with the radius of this circle now, and we're trying to draw a line through the space of all possible radii of these circles in order to separate it. So if I run this with a single neuron in the space of radiuses is able to draw a line through that radius space to correctly categorize these points, okay? So you can not only just feed all your data in and hope that you get the right thing, but you can also shape your data so that now there's a space that you're working in that needs fewer linearly separable elements in order to learn your data, okay? And someone asks, how do you choose the right amount of layers and the right amount of neurons for each layer? Well, what I've done, I don't know if you've been here for a while, but we've showed how to do this for very simple cases. Now, what I challenge you to do is go find the minimum network with the correct transformations to try and, categorize this thing. Because it's not easy, right? You may think that it has something to do with sine of x and cosine of x, or if you can somehow extrapolate this into the radius or how far you are along the spiral or whatever, but this one is much harder to categorize, okay? But what I wanted to show you there is intuitively how neural networks are working under the hood, how we could possibly start to choose how many hidden layers and stuff that we need, etc. But nowadays, when you say, okay, how many hidden layers, how many variables, how many weights do we need? Well, you just throw it at an RTX 3090 with 1 million weights, and then eventually it'll give you the right answer. Right? That's what a lot of people are doing because they don't understand the underlying theory of the neural nets to try and shape the network themselves. But when it does come to something as complicated as like facial recognition or object recognition, you do need a ton of hidden layers and a ton of weights and stuff like that. So I really encourage you to play around with this tool. It's quite powerful and it's quite good for visualization. All right. So I want to get back to the slides because I do have a couple of more slides for this that I want to get into. Okay, so let's go back to the PowerPoint. So that was the demo, and hopefully that showed, like in real time, sort of how neural networks work, right, and why they work. So neural networks are an approximation method they're a method for performing function approximation. Given a number of inputs and a desired outputs, they try and learn the function that computes the correct values, okay? And they do that by a bunch of dot products and a bunch of lines through spaces. That's essentially what's happening. So if you have an image classification problem, for example, you could have, well, Dave, how do you put an image into a neural network? Well, what you could do, and this is what some people do, is take an image of whatever size and then each pixel of that image might be black or white, a 1 or a 0. You feed that into the input layer of the neural network, which is of size 784, which is 28 by 28, I think. Yeah, 1 per pixel. You have some hidden layers in here with some amount of neurons, and then you have some output layers. And here, for example, our output layer would be 10 neurons, 1 for each digit, and then ideally our labeled data for this would have a 1 in the 7 column of the output, right? So our vector here would be values from 0 to 1, thinking how likely it is to be that digit for each of 0 to 9, right? So here, ideally, we would want to have a 7 come out. So training over time, it would have incorrect results and some correct results. It would use gradient descent, feed that back through the network. It's called back propagation. So there's feed forward and back propagation, where the weights are almost, they're iteratively refined using gradient descent, sorry, had a brain fart, in order to train this network. Okay. So, one thing that we could do, let's say that we wanted to learn something to help us compute something in this course, right? So, when we did assignment 2, sorry if this gives anyone PTSD from assignment 2, but what we tried to do was compute some heuristics, right? And so we used like the Manhattan distance or Euclidean distance in order to say this is a guess of the distance remaining from one point to another point. But what if we had some training data, and in the training data we could have our inputs, so an XY location for the start and an XY location for the goal, and then our target that we were trying to learn was the distance, right? And so what we could do was we could train a neural network to approximate the heuristic function, and then instead of using the really dumb Manhattan distance, we could use the neural net as the heuristic value, which would ideally be more accurate, right? And if we look back to something like A star, if we have the correct heuristic function, then we'll go straight towards the goal. So you could use a neural net for something like computing heuristics that search then uses as its guiding factor. So let's look at Alphago. So what did Alphago do? Alphago combined deep learning with heuristic search, a specific type of search called Monte Carlo tree search, which I think I'll cover in 2 lectures. So there were 2 neural networks that they trained. One was called a value network, and the other was called a policy network. And so the value network essentially said, how good is this state? So what they did is they took a bunch of human replays of Go. The input to the neural network was where every piece was, right? So it's the board state. And the output was whether or not the black player won or the white player won. And so whether or not player 1 or player 2 won the game, that was what the value network was trying to predict. So for example, the value network would say, oh, from this state, the black pieces are going to win 85% of the time. The other one was the policy network. So what they did for this one was they fed as the inputs a bunch of Go boards, and then the output was what move did the human player make in that situation. And so rather than just a single value of who should win this game, this one was one value for every piece on the board, and the output was how likely do I think I should move to that position? And so it used 2 networks, and then it used Monte Carlo tree search that was guided by these networks. So instead of having a heuristic function, so remember when we did alpha beta search and you had to write a heuristic function for Connect 4? Instead of sitting down by hand and trying to write a perfect Go heuristic, what they did was they watched a bunch of human replays, and they said, well, when we were in this state, this player won. We were in this state, this player won. And so they used a neural network to automatically learn that heuristic function that you wrote in assignment 3. So this is how this all starts to tie back in together, and we can see really cool stuff coming from this. And so DeepMind had thousands of professional human games to learn from, hundreds of thousands. The policy network, the input was the state, and the target was the move that the human performed. For the value network, the input was the state, and the target was who won the game from that state. We could also do something called learning from self-play with neural nets. So once it learned all it could from human, it started playing against itself. And it continued to learn, and it continued to get stronger. And now it learns, if it continues to get stronger, then as it keeps self-playing, it's learning from stronger opponents, and it gets stronger, even stronger. And it used forms of reinforcement learning in AlphaZero as well. So it combined neural networks, search, and reinforcement learning to make the best possible system. And so here's one way in which it helped heuristic search. Go has a very large branching factor. The board size is 19 by 19. And so on average, you might have hundreds of possible moves to look from. And if you remember back to Connect 4, even with just 7 moves, 7 times 7 times 7 times 7, maybe you're searching to depth, 8, 9 in your assignment. Humans have really good abstractions of what moves perform best at each state. So even though there might be 300 moves to choose from in a Go board, a human professional is only looking at maybe 5 or 6 of those moves, right? So what Alphago did was it learned a policy network, and so now it can narrow the heuristic search to only look at the moves that are in the policy network. So instead of searching all 300 possible moves, like you would have done in assignment 3 if we were using Go, it narrowed down the possibility to only a few really good moves. And so what it did was, now it can search much deeper in the game because it has a much better idea of what moves are good and what moves are bad. And the search also needed a heuristic function, right, to evaluate like how good this is. And it turns out that the value network provided a very good heuristic function for that. And not only that, but if you just took the policy network that AlphaGo learned, just the policy network without the search, it was already stronger than the strongest AI that had ever been created before that. So that's just a quick tease at how good neural networks can be for game AI. Next lecture, I'm actually going to go into a bit of the explanation of what deep neural networks are. And I said at the beginning that a deep neural network is just a wider neural net. That's not entirely true. There are some techniques that have become standard, like convolutions and max pooling and stuff. So we'll go into some of that stuff next time. And that's it for this lecture. And I hope you all have an excellent weekend.